Start.
Good morning, children. Welcome to webinar classes conducted by Christ Society. In today's circle class, we shall discuss very important topics, namely inverse points of the circle, inverse points with respect to the circle, and if the midpoint of the curve is given, the equation of the curve with respect to the circle, and third important point, relative positions of the circles. All these points once appeared in many times appeared in board of intermediate exam papers. So I request you all to please pay attention to our classes and do the given assignment so that you can get the command over these important topics, children. First, we shall discuss the inverse points. When do the given points are called inverse points with respect to the given circle? Children, here is the definition. The definition is also there in your textbook. The inverse point definition is in the page number 55. It's highlighted in the box. The definitions and the concepts is enough strength to do well in your mathematical problems. Definition: inverse points. Let's see with the center and R with the radius of the circle x is equal to 0. We are choosing a circle whose center is C and the radius is R. And the circle equation is denoted by x is equal to 0. In that case, the 2 points P and Q, are said to be inverse points. These points P and Q are said to be inverse points with respect to the circle x is equal to 0. Under what condition? If C, P, Q are collinear. The given points P and Q and the center of the circle C. C, P and Q are collinear. It means that all 3 points must lie on a same line. How should they lie? There should be a particular order. Where should be C, where should be P and Q, like that. What is that order? Such that they must lie on the same line, such that P, Q lie on the same side of C. If C is here, P, Q should be like this, or C and Q, P. They must be on both sides. There must be one side. Or C here, P, Q can be here. Or C here, Q, P can be here. Whether they can lie on right side or left side, it doesn't matter. But both P and Q must lie on the same side of C. And consider the product of the distances CP and CQ. The distance of C from P and the distance of C from Q, when multiplied, should be equal to the square of the radius of the circle. CP into CQ is equal to R square. So, first condition, the points must be collinear. 3 points. What are those 3 points? C, P and Q. Second, they must lie on the same straight line following one order. What is that? P, Q lie on the same side of C. And third, the product of the distances CP and CQ must be equal to R square. Following these conditions, we have a theorem. Let's see with the center and R with the radius of the circle x is equal to x square plus y square minus r square equal to 0. The 2 points P and Q are inverse points. Okay, the given points are inverse points. If and only if, means if the points are inverse points, it follows a condition. Q is the point of intersection of the polar of P with respect to x is equal to 0 and the line joining P and C. That is, this is a line. And this is a line here in the circle. What is this line? As we discussed, if C, P, Q are inverse points, they must lie on the same straight line. So this is that line where C, Q, P are on the same line. Observe, children. C, after that we have Q, after that we have P. In a sense, Q and P are on the same side of C. So that condition is also satisfied. And according to this statement, if P and Q are inverse points, then what is one of the point Q? is the point of intersection. Is it the common point of two lines? Yes. Which two lines? This is a point P. So Q lies on polar of P. And Q also lies on the line joining CP. If you have P here and if you have Q here, P lies on polar of Q. Is this clear, children? Then, if this condition is satisfied, the given points are inverse points. If the given points are inverse points, then Q is the point of intersection of the polar of P and the line joining CP. Is this clear, children? And we observe that what is this Q here? This Q is the port of the center of the circle to where? To the polar of P. Why we are discussing these many points? Because we have some applications like find the inverse point of -2, 3 with respect to the cell. X square plus y square minus 4x minus 6y plus 9 equal to 0. How can inverse of a point with respect to the circle using this? When they are inverse point, Q is the point of intersection of the polar of P with respect to S equal to 0 and the line joining P and C. We can make use of this. The inverse of the point P with respect to x is equal to 0 is foot of the perpendicular from the center of the circle x is equal to 0 to the polar of P. You can either find foot of the perpendicular from C onto the line or you can find the point of intersection. Anyone is same to find the Q. As you already know how to find the foot of the perpendicular, I am taking Q as a point of intersection of CP and the polar of P. So method 1 I am discussing. Method 2 is simple, using this mode just to find out the foot of the perpendicular from C to the polar of P. Let us see the method 1, children. We are interested in finding the inverse point of -2, 3. Given this is the circle. So let us write the given point and the center of the given circle. Now we need to find the polar of the given point. What is the formula to find the polar of a point with respect to the circle x is equal to 0, children? S1 equal to 0. What is the formula? X1 plus y1 minus of g 4x. So it is minus of 2 times x plus x1 minus 3 times y plus y1 and plus 9 equal to 0. What is x1, y1? The given point -2, 3. So x1 is -2 and y1 is 3. x1 is -2 and y1 is 3. On simplification, this 3y and -3 into y gets cancelled. And minus into plus minus 3 into 3 9. So it is -9 plus 9 gets cancelled. Then we will be remaining with x terms and constants. -2x and this is -2x minus 4x and minus into minus plus 4 equal to 0. Sorry. So it is -4x plus 4 is equal to 0. Taking -4 common, this is x minus 1 equal to 0 from which x is equal to 1. Take this as equation 1. So we got the polar of P. And what more we need is the line CP. The line CP. You know what is C here and you know what is P here. So can we find the equation of CP? Yes, we can. Using 2-point form of a straight line. Y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. So substitute in the formula. Y minus 3 is equal to 3 minus 3 by 2 plus 1 into x plus 2. Here C is the center of the circle. What is the center of the 2, 3? And what is P? The given point -2, 3. One is x1 by 1 and the other is x2 by 2. Substituting in the formula, we observe the right hand side. Is it 3? Yes. Then will it be equal to 0? Yes. 0 by defined value is 0. And 0 by defined value is 0. 1 minus 3 will be equal to 0, from which y is equal to 3. What is this? 3 is a straight line. One is horizontal line and the other is vertical line. And the point of intersection of these two lines is a common point. What is the common point? 1, 3. Okay, we have horizontal 1 and vertical 3. Both meet a point. What is the point? The point where x is equal to 1 and y is equal to 3 is satisfied. Therefore, that is point is 1, 3. What is this 1, 3? Is nothing but the inverse point of -2, 3 is 1, 3. Is that clear for the given point -2, 3? With this, you can also solve this problem by finding okay. Okay, so due to the technical problem, video was not available for some time, children. So this problem is already solved in the textbook, children. You can find one more example also, finding the one more method of the same problem, children. Next, our important concept is equation of the curve with given middle point of the curve. Let us discuss the statement. And the question on this concept is also asked many times in the public exam, children. What is our concept now? We have a circle S is equal to 0 and a point which is the midpoint of a curve. And we can find out the equation of that curve. So given x1, y1 as the midpoint of the curve and equation of the circle, let us see the precision. How to find the equation of the curve. Statement. Let us take the statement, children. Equation of the curve with given middle point. When are we writing equation of the curve? When we know the middle point of the curve. Let us take the statement. If P x1 comma y1 is the midpoint of the curve, is the midpoint of the curve AB, and this AB curve is other than diameter. Okay, we are not taking AB as a diameter, some other curve of the circle. Let us see what happens if it is diameter also. Of the circle. What is the circle? X square plus y square plus 2gx plus 2fy plus c is equal to 0. Then the equation of secant AB, equation of secant AB is S1 equal to H double 1. Now we need to prove this answer. S1 is equal to S double 1 statement. Children, let us take the given point. Given point P as x1 comma y1. And what more is given in the question? Circle. Given circle. What is given circle, children? S is equal to x square plus y square plus 2gx plus 2fy plus c is equal to 0. Then let us draw the diagram, children. This is the circle and we have a curve AB. This is secant AB where the secant is intersecting the circle at A and B. Now we are talking about only the curve. If we know the midpoint of this curve, then we can find equation of this line AB. What is its equation? S1 is equal to H double 1 is the proof that we are going to do. How can we do this? You can understand. We need to find out the equation of this straight line. Let us take some important concepts that we have studied in our earlier geometry of school age. If we have a center C, if we have a center of the circle as C, and this is curved AB, only this portion, only this part is AB, then the perpendicular drawn from center onto the curve bisects the curve. The perpendicular drawn from the center of the curve, the bisects the curve. Then AB is equal to PB and the last CB will be perpendicular to AB. Using that concept, we'll find the slope of CP, children. Because C is the center of the circle and P is the point given, the midpoint of the curve. Can we find the slope of CP? Yes, we can. How can we find the slope of CP? Using the formula y2 minus y1 by x2 minus x1. y2 minus y1 by x2 minus x1. This slope of CP, when taken reciprocal with minus sign, gives us the slope of AB. Isn't it, children? Why? Because AB is perpendicular to CP. When we got the slope of AB and when we know a point on AB, Can we find the equation of AB, children? Yes, we can find. What is the formula? Y minus y1 equal to y2 minus y1 by x2 minus x1 into x minus x1. Then that equation, when simplified, will take the form x1 is equal to x11. Just go through this theorem given the textbook. This I have provided you the outline why s1 is equal to x11 will be the equation of this curve. And do a problem on this concept. Children, after this we have an example problem. Find the midpoint of the curve intercepted by. Using this concept, we will do some problems. We have a point A and a point B on the circle, and equation of AB is given, and circle equation of circle is given. X is equal to 0 is given, and equation of AB is given. Now he is asking us to find out the midpoint of this curve. How can we find the midpoint of the curve, children? We infer that the midpoint of this curve P is the foot of the perpendicular drawn from center onto the line. So use the formula of foot of the perpendicular that we have studied in the first year. What is the formula, children? H minus x1 by a is equal to k minus y1 by b is equal to minus of ax1 plus b by 1 plus b by a square plus b square. Using that, we can find out p. It is already solved in the textbook. I am just explaining the concept because this concept is not covered in the exercise problems. And another very, very important question once appeared in the Bodhan intermediate is find the locus of the midpoints of the curves of contact x square plus y square is equal to a square from the points lying on the line lx plus my plus n equal to 0. Let us solve this problem. Let us take example 2, page number 58. Page 58, example 2. Children, if the board is not clear, I request you all to kindly look into the textbook which is already solved. And this problem is very important. If you understand the geometrical interpretation only, then you can understand the algebraic explanation provided in the textbook. Find the locus of midpoints of the curves of contact of x square plus y square is equal to a square from the points lying on the line lx plus my plus n equal to 0. Solution. Let us write the given circles, children. And given line. Let us discuss what is the relation between this point and this line, why this circle and this line, why they are given in the question. The locus of midpoints of the curves of contact. So we need to find out curve of contact of this circle from the point. And for that curve of contact, we have to find the midpoints. The locus of such midpoints we need to find out. And the curve of contact of this circle with respect to which point? From the point lying on this line. So let us take a circle and let us take a line lx plus my plus n equal to 0. And let us take a point P, and if you have a curve, and then find the curve of contact, Then midpoint of this curve, if this is A and this is B, and midpoint of this curve, suppose it is some S, because we already picked, let us take this as R. Midpoint of this curve, if it is x1 y1, can you find the equation of this line, children? Yes, using which formula? S1 equal to S double 1, because you know the midpoint of this curve. Using S1 is equal to S double 1, you have the equation of this curve. And you need to find out the locus of the midpoint of this curve. Isn't it? And from where this curve of contact has taken from a point P. Where is this point P? This point P is on the line Lx plus My plus N equal to 0. Is this clear, children? And we have to observe one very important point that we have discussed in our previous classes, that if P is the exterior point of the circle, then the polar of P will intersect the circle. And the polar of P will coincide with curve of contact of P. So in this case, the line S1 is equal to S double 1 is the polar of P. Using these important relations, it is the coordinate as the combination of the top X polar and the curve of contact of P. Given line Lx plus My plus N is equal to 0. Because he is talking about the locus, let us choose a point on the locus. Let P x1 y1 be a point on the locus. Then P satisfies the geometric condition. P satisfies the geometric condition. What is the geometric condition, children? Satisfied by P? That midpoint of the curve of contact of the circle. P is the midpoint of curve of contact of S is equal to 0. From the points, just write the given lying on. Where are the points lying? L is equal to 0. Then we need to find out the curve of contact. How can we find curve of contact when midpoint is given? Just now we have seen this statement. Therefore, this equation of this curve of contact or this curve is S1 is equal to S double 1. Now write what is S double 1. Equation of this curve of S is equal to 0 is S1 equal to S double 1. What is S1, children? X1 plus Y1 minus A square is equal to X1 square plus Y1 square. Now rearranging the term. X1 square minus A square. Minus A square plus A square gets cancelled. So it is X1 plus Y1 is equal to X1 square plus Y1 square. Now we got this equation. This is polar of P. So how can we find the P? It's to find pole. So pole of line 1 is, we have a formula minus A square radius minus A square x coefficient x1 by x1 square plus y1 square minus A square L by N. X minus A square M, that is y1 by x1 square plus y1 square. And this is the pole of this line. Where is that point P pole? Is on the line Lx plus My plus N equal to 0. This point is on Lx plus My plus N equal to 0. So in place of x, substitute the x coordinate. In place of y, substitute the y coordinate. We get the required equation of locus of P. Implies L into minus A square x1 by x1 square plus y1 square plus M into minus a square by 1 by x1 square plus y1 square plus n equal to 0. On simplification of which we will get the required equation of locus of t. So it's L into minus a square x1 plus n into minus a square y1 plus n into x1 square plus y1 square is equal to 0. Taking minus common and a square common, a square into nx1 plus my1 plus n into x1 square plus y1 square is equal to equation of x1 y1 is just drop x1 and drop the suffixes children. Is a square into lx plus my plus n into x square plus y square equal to 0 is a required equation of locus of t. With this, we have finished the important concepts to be covered in exercise 1D. Today's homework is complete the exercise 1D. Dear children, let us take some important concept of next exercise. Dear children, so far we have discussed the relative position of a point with respect to the circle x is equal to 0. This is point and this is x equal to 0. The point may be in the exterior plane of the circle, the point may be on the circle, and the point may be in the interior plane of the circle. So there exist three different positions for a point with respect to the circle. Similarly, there exist three positions for a straight line with respect to the circle s is equal to 0. What are those? The line may not touch the circle, or the line may completely be in the exterior plane of the circle. We got the position, relative position of the line with respect to the circle s is equal to 0 in terms of points of intersection. No point in common in this case, but the line L is equal to 0 and the circle s is equal to 0. In the next case, we have one point in common. Okay. In the next case, we have 2 points in common. So there exist three positions again. No points in common, 1 point in common, and 2 points in common. We have seen different conditions. Cp square minus r square greater than 0 is equal to 0, less than 0. Accordingly, the point lies outside the circle, on the circle, and inside the circle. Here is also whether the perpendicular distance d greater than r, or d is equal to r, or d less than r. Accordingly, the line lies outside the circle or on the circle, or the points and line have no points in common, or 1 point in common, and 2 points in common. So these are the algebraic conditions required for this geometrical interpretation for the points as well as lines. Now, this session we try to get the geometric interpretation of the relative positions of the circles. So far, one circle has 1 point, and one circle has 1 line. Now, let us discuss the relative positions of 2 circles. Relative positions of 2 circles. Let us take 2 circles, children. The objects which are in the circular shape. I'll just maintain them in enough distance. Let us place them separately, and we will try to bring them close. So this is the first position where the circles do not touch each other. The circles do not touch each other. This is case 1. And case 2, let us bring them close. Now here is a case, they touch each other. The circles touch each other. So let us note that case wherever we are finding different case. And what is third case? Bring more closure. Okay, from this to we are going this, and then we can bring them more close. Then circles will intersect. The two circles intersect. Then there exist 2 points, no points in common, 1 point in common, and then 2 points in common. And let us see what is the fourth. First case, no points in common. Second case, 1 point in common. Next, 2 points in common. Next, still moving. One circle may completely lie inside the other circle, touching at one end. See, the bangle is inside this. Okay, is the bangle inside this? Yes. Then the circles touch each other internally. There will be 1 point in common, but one circle lies completely inside the other circle. And bring more close, children. One lies inside, but no point in common. So these are the different cases. There is no point in common. Okay. And we have another subcase if they have same centers. There are different possible relative positions of two circles. One circle is in the exterior plane of the other circle. One circle touches the other circle, 1 point in common. And one circle intersects the other circle. So 2 points in common. One circle touches the other circle. See, here also 1 point in common, and here also 1 point in common. What is the difference? They touch each other externally. These two circles, S is equal to 0 and S dash equal to 0, touch each other externally. The two circles touch each other externally. Then they touch each other. But where is the point of contact? In between the centers of the circle. The point of contact is in between the centers of the circle. Similarly, the two circles, one circle lies in the interior plane of the circle, and then they touch each other. And here, the one circle completely lies in the circle, do not touch. Here, one completely lies in the other circle, they do not touch but concentrate. These two conditions come under the title, one lies in the interior plane of the other circle. Is this clear, children? Now, let us discuss these cases in detail with reference to the distances. Which distances? When it is possible. That is decided by the distance between the centers of the circles and their radii. If R1 is the radius of the first circle and C1 is the center of the first circle and C2 is the center of the second circle and R2 is the radius of the second circle. And let us discuss each case separately. Let us draw. Children, small announcement. Due to some technical problem, yesterday the class was not comfortably. Though I have completed yesterday's syllabus, I felt there was some noise and disturbance, so I uploaded a new video after our session, and it's there on YouTube. You can find the Circles class 10 link, class 11 link in the YouTube, children. And if C1 is a center and C2 of the first circle and C2 is a center of the second circle, R1 is the radius of the first circle and R2 is the radius of the second circle. I will try to take it outside C1, C2 and just join C1 and C2. And observe that, suppose I'm imagining, I'm just transforming that length. This is R1 and this is R2 from here to here, for example. If I take these values on a straight line, if I compare, this is R1, this distance is R1 and this distance is R2. But this length is C1 from here to here, C2. So this distance C1, C2 is greater than R1 plus R2. Join of R1 is still from here to here only. Join of R1 here only. So this length is more in C1, C2. So the condition required for the circles to be apart so that they don't have any common point. One circle lies in the exterior plane of the circle. One is completely outside the other circle and they do not have any points in common. Is possible when the distance between the centers of those two circles is greater than sum of their radii. So C1, C2 is greater than R1 plus R2 is the required condition for the two circles S is equal to 0 and S dash is equal to 0 to be apart and have no points in common. This is case 1, children. And let us take case 2. What was the case 2? You can observe the case 2 by bringing the circles together. So they touch. These two circles may have the same radius or may not have, children. One may be bigger than the other or they may have equal radius. Let us take C1 as the center of the first circle and C2 as the center of the second circle. Let us join the centers of the circle. And from here to here it is R1. And from here to here it is R2. Suppose P is a point in common. PC2 is R2, PC1 is R1. So C1P plus C2P is equal to C1C2, which implies R1 plus R2 is equal to C1C2. So the distance between, or rearranging in the order, C1, C2 is equal to R1 plus R2. Is a condition required for C1 for these two circles to touch each other externally. To touch circles externally. One circle will be outside the other circle, but they touch from outside like this. Observe, children, when two circles touch each other externally, the point of contact exists. One point of contact exists. And this point of contact P is on the line joining C1, C2. P is on the line joining C1, C2. In other words, P divides the line joining C1, C2 internally in the ratio of their radii R1, R2. Now, let us take case 3. Again, I will take the circles more internal, then they intersect. Again, taking C1 as the center of the first circle and C2 as the center of the second circle, then it is C1, C2. And this distance is taken as R1 and this distance is taken as R2. And observe, children, this distance from here to here it is R1 and here it is R2. So, the difference R1 minus R2 from here and from here. Let us take. Sir?
Conclude.
Sir?
10:45 is going on.
Okay, sir. So mod R1 minus R2 is less than C1 C2 is less than R1 plus R2 is a required condition for the circles to touch externally. Sorry, to intersect at two different points. And we have the other condition when one circle will lie completely inside the other circle and touch internally. Then the point of contact is external. And the condition required for it is C1 C2 is less than mod R1 minus R2. And this is fourth condition. And fifth condition is when the circle lies inside C1 and C2. Can you tell me what is the geometric condition required for the circles to touch, to be inside the circle but do not touch? Is your homework. Sorry, 1 minute, children.
Including.
Let us discuss these two cases tomorrow. You please go through these concepts and do the related problems given in the exercise. Thank you all. Have a great day, children.